Hello, peeps. We're going to section 6.2. Well, let's start with t. T is a linear transformation from R3 to R3, and the definition of it, of the function, is that t of xyz is xy0. This is actually, as we mentioned previously, is called a projection onto the xy plane. But anyway, my point is like this. Suppose I want to look at what different ways that I could get 0 from this transformation. Well, 005 is going to go to 0 because these two zeros stay. There's the two zeros are going to stay, and then the 5 is going to turn into a 0. So t of 005 is equal to 000. T of 007, for your James Bond fan, is going to be 000. And of course, t of 00 is going to be, and it doesn't take too long to realize that if anything, 00k is going to go into 000. Now, 000, I'm mentioning that because that's the 0 vector. So when you look at the set of all elements of the domain that go into the 0 vector in the range, codomain, whatever you want to call it, that set is referred to as the kernel of the linear transformation. Definition of kernel. So if t is a linear transformation from v to w, two vector spaces, then the set of all vectors v in v that satisfy t of v equals 0 is called the kernel of t. In this case, of the example we gave, the kernel of t was the set of all vectors of the form 00k. Let's look first at two very simple examples. If you have the 0 transformation, that's with t of v equals 0 for all v. Well, the kernel of t is the entire domain v, because everything in the entire domain goes to 0. And if you look at the identity transformation, which is that t of v equals v, well, in that case, the kernel of t is just the 0 vector, because, well, you can figure that one out. So it's interesting. Here, the kernel is just a 0 vector. Here, the kernel is the entire vector space. And here, the kernel is this 0k, which, by the way, 00k could be rewritten as k times the basis vector 001. I guess what I'm hinting at is that the kernel of any vector, the kernel of any linear transformation, is always going to be a vector space. And I'm going to prove it right now, very simply. The kernel of t is a subspace of the domain v, meaning t goes from v to w, and it's a subspace of the domain. Well, remember, if I want to prove something's a subspace, I just have to show that it's closed under vector addition and scalar multiplication, and that is not too hard to show at all. Let's just let u and v be vectors in the kernel of t, and c is a scalar. So t of u plus v is equal to t of u plus t of v, which is 0 plus 0, which is a 0 vector. So we see that u plus v is in the kernel of t because t of u plus v is equal to the 0 vector. Hence, kernel of t is closed under vector addition. Similarly, if we look at cu, so t of cu is equal to c times t of u, which is c times 0, which is 0, which means that cu goes to 0. So if u is in the kernel, cu is also in the kernel, which means the kernel is closed under scalar multiplication. Hence, the kernel is a subspace. The end.